We have mentioned earlier that uniform motion occurs when a body is exposed to gravity. I should possibly have said that more correctly it is exposed to gravity alone. In this situation, as you will learn later, an object would accelerate until it was stopped by another force. If there was no such force, this object would accelerate to an infinite speed, in classical physics at least. However, there is always an opposing force on Earth, that of friction or drag. When an object falls on Earth, it is pulled towards the centre of mass of the Earth, which is located near to the geometric centre of the planet. Wherever we are on the surface of the planet, the centre is always below us, so gravity pulls all objects downwards from the perspective of someone living on the surface. From the perspective of someone living in space, it would appear that people towards the South Pole are pulled upwards, and those towards the North Pole are pulled downwards. As very few of us live in space for a protracted period of time, we tend to know that gravity pulls things down. This is the overwhelming long-range force on Earth, and would cause objects to increase in velocity until they hit the surface and are stopped. However, these objects do not fall through a vacuum, and so their motion is opposed during descent. The more there is to oppose the motion, the lower the overall force, and so the slower the object will travel. Towards the surface of the planet Earth, we can assume that two things are constant: the thickness of the atmosphere and the density of the Earth. The density of the Earth beneath our feet affects the concentration of mass, and so the gravitational pull. The variation in density is very small around the world, but still measurable with devices called accelerometers. We average out these small differences to a value for acceleration close to the Earth's surface as 9.1 meters per second per second. That is to say that in 1 second the velocity of an object will increase by 9.81 meters per second. If an object has no initial velocity, after 1 second it will have 9.81 meters per second. After 2 seconds it will have 19.62 meters per second, etc. This value stays constant as long as the overall force on the object stays constant. The gravitational force of the Earth doesn't change, but the resistive force of the atmosphere does. Travelling through a material generates resistance. Imagine running through air as you normally do. Now imagine trying to run through water at the swimming pool. It is a lot harder because water is a lot more dense. The more dense the material, the harder it is to run through. Air is denser than a vacuum, so air gives us resistance. This resistance provides a force to oppose the force of gravity. The faster you try to move through a material, the more this material generates a force to oppose your motion. This is why when a car travels through a puddle at high speed, the water travels further into the air than when it travels through at low speed. The longer the object is exposed to the force of gravity, the faster it will become. Initially, this speed generates a small resistive force from the atmosphere. As the speed increases due to gravity, so does the resistive force due to the air. This means that instead of 9.81 meters per second every second that our object was experiencing gravity, it now experiences less than this. It is still accelerating towards the ground, but the air makes this acceleration lower. As the object's speed increases, the resistive force increases, reducing the overall force on the object and decreasing its acceleration. Eventually, the force of gravity pulling the object down will be equalized by the resistive force of the air against this motion. At this point, the acceleration on the object is zero, and it is said to have reached terminal velocity or terminal speed. This is not one velocity for one object, merely one velocity for one shape of object. The bigger the resistive force, the bigger the force that can be ultimately oppose gravity, and the quicker it can reduce the acceleration to zero. The bigger the sail, the more air it can capture, and the more resistance the object will have. By falling from a plane with a parachute on, you are not diminishing the force of gravity pulling you towards the Earth, or the force required to cancel this force out. You are merely decreasing the time it will take this velocity, and so reducing your terminal velocity. In other words, if you fall out of a plane with a parachute on, you have a greater resistive force, and this will equalize the gravitational pull much quicker. If, however, you open your parachute after you've reached the terminal velocity, you will momentarily increase the upward force, so it is greater than a downward force. This means that temporarily the force acting upon you is upwards overall. The force upwards is greater than the force downwards. This leads to a reduction in your terminal velocity, as the resistive force is directly linked to your speed and area of opposition. Once you've slowed your velocity downward enough, you will continue to fall at a steady rate, but at a slower velocity. This means you can change your terminal velocity to one which means you can land and not break anything. Finally, I shall address a problem of the video age, namely the appearance of a parachutist flying upwards when activating their parachute. What happens here, or what appears to happen in these videos, is that the parachutist moves upwards in the sky rather than continuing to fall at a reduced rate. The reason for this is that instead of one person falling through the atmosphere, there are two, the person being filmed and the person filming. The camera operator is busy filming the person in freefall. They themselves are also in freefall at the same rate as the person being recorded. They have the same terminal velocity, so they appear stationary relative to each other. When the person being filmed pulls their parachute, the force on them upwards is greater than downwards, and so they slow down. The illusion of reversing direction, rather than slowing down, comes from the camera operative. They continue to fall at the same speed as previously, so hurtle past the person being filmed.